Our universe is constantly expanding, stretching the very fabric of space like a balloon, rising silently into a calm sky. This ongoing growth makes it nearly impossible to draw definitive borders or determine its true size across the endless horizon. An invisible force called dark energy drives this expansion, pushing galaxies apart like leaves drifting down a slow-moving river. As time advances, galaxies move away from each other at increasing speeds, much like boats being pulled by a powerful current through a vast, empty void. To measure this motion, scientists rely on a phenomenon called redshift, similar to tracking a distant flare moving through the night. The James Webb Space Telescope has transformed our understanding of this motion. With its infrared vision, it peers through cosmic dust like headlights slicing through a dark tunnel. Before Webb, the Hubble Space Telescope provided the deepest images of space, majestic yet limited, like paintings hung on a black wall. Hubble couldn't see certain hidden details in the infrared spectrum, similar to trying to see through fog with an ordinary lens. Positioned at Lagrange point 2, the James Webb avoids Earth's interference and captures sharp images, like a camera above a city's glare. It has revealed galaxies born just 300 million years after the Big Bang, tiny lanterns glowing in the vast distance. These ancient galaxies challenge our models of cosmic evolution, forcing scientists to rethink how the early universe was structured. Experts like Brian Cox and Neil deGrasse Tyson remind us how small we truly are on this immense stage. Cox often remarks that the visible universe is like a single grain of sand on an enormous beach. The observable universe stretches about 93 billion light-years across, a distance too large to fit on any map. Even so, that's only the region from which light has reached us. Beyond this lies the unobservable universe, cloaked in mystery behind a cosmic curtain. Within the visible cosmos, scientists estimate there are around 2 trillion galaxies, each teeming with stars that shine like distant lamps. These staggering numbers come from deep sky surveys that stared into quiet pockets of space for days. In 1995, Hubble focused on a small area and uncovered thousands of galaxies in a single view. Later surveys confirmed that galaxies are arranged in a massive cosmic web, threads stretching across space and sculpted by gravity. This web is composed of filaments, voids, and clusters, shaped like clay, molded by invisible forces. Though our solar system feels vast, it is minuscule compared to the full span of our galaxy. If a car traveled nonstop at 70 miles per hour, it would take 15 days to circle Earth's equator, 5 months to reach the Moon, and 63 years to get to Mars. But even those journeys are tiny compared to the distances between stars. Voyager 1, launched in 1977, didn't leave the solar system until 2012, after traveling more than 14 billion miles. Yet it still hasn't reached the Oort cloud, a distant, icy shell. While light travels at an astonishing 670 million miles per hour, even it takes 8 minutes to reach Earth from the Sun, and 4.3 years to reach Alpha Centauri, our closest stellar neighbor. At Voyager's speed, that journey would take about 70,000 years, like crossing a desert with no end in sight. This is why human interstellar travel remains a dream beneath our glowing sky. Even Proxima Centauri b, the nearest known exoplanet, lies far beyond our current reach. The Milky Way contains around 300 billion stars, each surrounded by silent, spinning planets. The galaxy itself stretches 100,000 light-years across, like a giant whirlpool drifting in the cosmic ocean. Earth orbits 26,000 light-years from the galactic center, positioned in the Orion Arm. At the heart of the Milky Way lies Sagittarius A, a supermassive black hole around which stars orbit like sparks spinning around an invisible fire. Our solar system completes one galactic orbit every 230 million years, a long journey around a silent, celestial carousel. Beyond the Milky Way lies the Local Group, a cluster of 54 galaxies nestled in a small corner of the universe. Our closest neighbor, the Andromeda Galaxy, lies 2.5 million light-years away and is moving toward us at 68 miles per second. This cosmic collision will occur in about 4.5 billion years, merging both galaxies into one giant elliptical form. Despite the galactic crash, stars are so far apart that they will likely pass by each other like snowflakes drifting in the wind. The merger will, however, ignite new star formation, sparks born from the clash of titanic systems. Galaxies tend to cluster together in larger structures, like the Virgo supercluster, home to about 1/500 galaxies. This supercluster is part of the much larger Laniakea supercluster, stretching 520 million light-years across, like an enormous cosmic net. The name Laniakea means immense heaven in Hawaiian, a fitting title for a structure so vast it encompasses an entire region of the sky. These superclusters form the skeleton of the cosmic web, connected by filaments of dark matter that act like bridges over an invisible sea. Between these filaments are immense voids, vast regions with almost no matter, some spanning millions of light-years. Scientists estimate around 10 million superclusters exist in the observable universe, each one housing countless stars. But all this visible matter accounts for only about 5% of what's really out there. The rest lies hidden. Dark matter makes up about 27% of the universe, acting as an unseen scaffold that holds galaxies in place. While dark energy, making up the remaining 68%, pushes the universe outward, like wind inflating a vast parachute. This ongoing tug-of-war between dark matter and dark energy shapes the universe's ultimate fate. Cosmic voids, some as large as 330 million light-years, challenge our understanding of matter's distribution. These silent spaces suggest that our current physics might be incomplete. Meanwhile, filaments of gas and dark matter stretch across the universe like veins through a living body, channeling galaxies into clusters like seeds planted in a cosmic field. Neutron stars, incredibly dense remnants of massive stars, are so compact that a single teaspoon would weigh 1 billion tons, more than a mountain squeezed into a seed. These stars spin rapidly, flashing beams of light like cosmic lighthouses. When two neutron stars collide, they create gravitational waves, ripples in the fabric of space-time detected on Earth by instruments like LIGO. These waves confirm Einstein's theory that space itself bends and flexes like a blanket being shaken. Such collisions also forge heavy elements like gold and platinum in a celestial forge. Black holes bend time and space, acting like drains that pull everything, even light, past the event horizon. A point of no return. The largest black holes, power quasars, brilliant beacons fueled by spinning disks of matter. These quasars shine brighter than entire galaxies, their light traveling billions of years to reach us. The James Webb telescope has spotted some of these ancient giants, glowing like stars above a sleeping village. Their existence shows that the universe formed complex structures faster than we once thought, galaxies taking shape like clouds before a sudden storm. All of this hints that the universe may be older and larger than previously imagined. Beyond our visible cosmos, many believe there could be infinite universes, a concept known as the multiverse. According to this theory, each universe could be like a bubble in a vast sea, some following different physical laws, like rooms in a mansion with unique rules. Some might have no gravity, no stars, only quiet emptiness, while others may be teeming with galaxies more beautiful than anything our telescopes can see. This idea arises from inflation theory, which suggests the universe expanded faster than light during its first instant. It also fits with string theory, where reality is made of tiny vibrating strands, and with the idea that our universe is a brain, floating in higher dimensional space. Collisions between such brains could spark new universes, like raindrops falling into a cosmic pond. We may never see these realms directly, but quantum effects and advanced mathematics suggest deeper realities behind the curtain of space and time. Back in our known universe, life depends on finely tuned balances: temperature, gravity, time, too much or too little of any, and life would vanish, like smoke swept away by a cold wind. This delicate balance leads some to believe in a cosmic design, while others see it as a lucky throw of the dice. Either way, Earth's story is a rare one. A blue dot orbiting a quiet star, formed from stardust, the remains of ancient supernova. Life began in warm oceans, spread through forests and deserts, and eventually looked up to the stars. Now we build machines to explore and ask where we came from. Our radio signals drift outward, like whispers in a sleeping house, possibly to be heard one day by another intelligence. We search for alien life using instruments like the Webb telescope and robotic rovers that explore distant worlds. The TRAPPIST-1 system, with its 7 rocky planets, some in the habitable zone, is one target. We measure their atmospheres, their heat and shadows, looking for signs of life. Mars, once home to rivers and lakes, now lies dormant, waiting for our machines to read its dusty past. Moons like Europa and Enceladus hide oceans beneath ice, possibly warmed by internal heat and home to life in deep, dark waters. Each discovery adds to a story written across light years of quiet space. The more we learn, the more we realize how much remains unknown in this cosmic library. Here on Earth, we still watch eclipses, comets, and auroras, sky poems that dance across snowy landscapes. We build satellites and telescopes, silent eyes orbiting above,